The recorded speaker is John Peterson, Stanford University, Field of Plasma Physics. Advisor is Siegfried Glenzer, and he's completed residencies at Lawrence Livermore National Laboratory in 2021 and 2022.
All right, thank you so much for attending today. My name is John Ryan Peterson. I am a recently graduated Stanford physics student and conducted a lot of my work also at SLAC National Laboratory, and as part of the LRGF Fellowship, performed 2 residencies at Lawrence Livermore National Laboratory. And so I'm excited to tell you today about magnetic field and radiation production in laser-driven electron beams. In particular, 2 projects that I worked on during my residencies at Lawrence Livermore. So before I get started, also I would like to thank my advisors, first and foremost, Siegfried Glenzer and Federico Fiuza, as well as the many collaborators that I've had the good fortune to work with, both within Lawrence Livermore and at other institutions, and especially the DOE for financial support and computing resources. So this work is going to be primarily computational with an experimental component as well, but a large computational effort which was performed on several DOE supercomputers. So the main motivation for what I'm going to present today is understanding particle acceleration and radiation emission in both astrophysical plasmas, such as in supernova remnants, an example of which you see here on the left, and in high-power laser plasma interactions. So on the right is the Omega laser in Rochester, New York, one of the most powerful lasers in the world today. And so if I can turn your attention back to this picture on the left, what we see here is the Cassiopeia A supernova remnant. In this image, this is an X-ray composite image. The different colors in this image correspond to different X-ray energies. And the blue color specifically is emitted by what are called non-thermal or superthermal electrons. So as this expanding blast wave emits X-rays through a variety of mechanisms, it turns out that the blue X-rays here are emitted by particles which have a significantly higher energy than the thermal temperature. And so there is some process in these very high energy astrophysical accelerators that is accelerating a small portion of electrons to much, much higher velocities. And this can convert tens of % of the entire supernova energy into these superthermal electrons and ions. And so understanding this process has been a long time, multi-decadal effort. And on the right, a better understanding of particle acceleration and radiation emission in laser plasmas can lead to very important compact X-ray and ion sources, which I'll get into in a minute. So in particular, in gamma ray bursts, which is a type of supernova, these supernovae are thought to occur when a central engine, such as a black hole that's formed when 2 neutron stars collide, during this formation process, this progenitor emits a jet of very high energy relativistic plasma. And so you can kind of see that beam-like structure being emitted from the central engine in this diagram on the left. And in the process of this ejected plasma interacting with the surrounding medium, like the interstellar medium, as it pushes on this interstellar plasma, it can accelerate particles to very high energies, emit high energy X-rays and gamma rays, and visible light and radio waves as well. But the process by which this occurs is it's a very exotic process, because it turns out that the particles are so far apart and the densities are so low here that collisions between particles are actually very rare. So in this collisionless regime, this ejecta, as it's interacting with the surrounding medium, needs to somehow couple to this medium and push on it by self-generating spontaneously electromagnetic fields through plasma instabilities. So instead of having particle-particle collisions that are causing these shock waves to form, you have these collective plasma waves that spontaneously generate. And in the process, because you have these plasma waves generating strong electromagnetic fields, the particles that are accelerated will also bend in these electromagnetic fields, and in so doing, they emit synchrotron radiation. And so that is the important diagnostic that we have that shows us that these objects are accelerating particles to very high energies, is that they are then radiating very high energy X-rays and gamma rays. And so understanding the process by which these electromagnetic fields are formed and self-generated has been a long process and an intense effort in high energy astrophysics. And so it turns out that we can actually use high power lasers to kind of recreate, in some aspects, the conditions found in these high energy accelerators. So both linear accelerators, such as the linear accelerator at SLAC, the Facet 2 facility, or high power lasers like Omega EP, can accelerate relativistic electron beams. So in the first case, up to several GeV or giga electron volt energies. In the latter case, mega electron volt energies, still both highly relativistic. And through some exciting developments in roughly the last decade, these facilities are now able to accelerate large enough volumes of plasma to study some of these collective plasma instabilities and effects that are thought to be important in gamma ray bursts. So my first project that I'm going to show you here is investigating how we can use this laboratory generated electron beam, and by sending it through a background plasma like a gas jet, which you see here on the right, you can kind of reproduce this in some aspects the gamma ray burst, where you have a high energy relativistic charge striking this cold, dense interstellar medium. And so you can investigate the plasma physics in this regime. But one important difference here is that our beam has a finite size. So the size of the beams in a gamma ray burst are many, many orders of magnitude larger than the scales at which these plasma instabilities and processes operate. So an important consideration is to understand if we have a beam where the duration is much, much shorter, the spot size, the width is much shorter, and it's now comparable to the sizes and time scales of these plasma processes, how does that impact the plasma physics at play? And so I conducted a series of particle and cell kinetic plasma simulations. What you see here is a density profile at 3 different times of a laboratory scale electron beam striking or propagating through a background plasma like you would find in a gas jet. And so on the top row here, we have these 3 different time slices of cross sections of a beam. The beam is propagating to the right. You see here a plot of the beam density. And in this top row here, the beam is very wide. So you can see it's in these units. So the distance units here are plasma skin depths. In this case, it's about a micron. So it's about 2 microns long and about 20 microns wide. And as this beam propagates through the background plasma, it spontaneously breaks up into these little filaments, which you can see these kind of pencil-like filaments. And that in the process of doing so, it creates magnetic fields around each of these filaments. And so this process of filamentation and magnetic field generation is one of the primary rules by which gamma ray bursts are thought to spontaneously produce these magnetic fields and radiate X-rays. On the other hand, if your beam becomes a little bit longer, so in this bottom row, we have here a beam which is about 20 microns long, much longer and much narrower. And you can see that in this case, you still have these spontaneous modulations form at later time, but it turns out that you generate much stronger electric fields in this case. So both of these processes, these 2 instabilities, the filamentation and the oblique instability, are important in astrophysics. And through this work, I was able to investigate to demonstrate the threshold at which you transition between these two instabilities. And so you can kind of pick by choosing different beam shapes and background densities, you can study both of these instabilities in the laboratory and use this to validate astrophysical models. So in my work with my collaborators, we found that the growth rate of these instabilities depends significantly on the duration of the beam. And in addition, the spot size or the width of the beam affects the competition with self-focusing. So if your beam is too narrow, then instead of breaking up into these filaments or these oblique modulations, then the beam will just self-focus into a single filament, and then you can't study the same plasma processes. So with both of these considerations, I developed a threshold, a criterion here, which takes into account the beam spot size, sigma perp, and the duration, sigma x. And so if the beam shape satisfies this criterion, then the beam will be unstable dominantly to plasma instabilities and not to the self-focusing process. So then applying this in a 3D simulation, we have the results here. So a large part of the motivation for this is also not only to study these instabilities, but also to harness their spontaneously generated magnetic fields for high energy synchrotron X-ray emission. So in this cartoon on the top left, we have kind of a schematic of how this might work, that you have a high power petawatt femtosecond laser striking a gas jet. And this interaction will accelerate an electron beam through the laser wake field process. And then this high energy electron beam will then strike a secondary gas jet that is much denser. And during this second interaction, it becomes unstable to these plasma instabilities and can radiate high energy X-rays. And so in my 3D simulations of this interaction, I have here two plots on the bottom. On the left, I have kind of a cross section. This time, in this simulation, the beam is propagating into the page. It's a full 3D simulation. And you can see that the beam still breaks up into these filaments. Now we're looking at kind of the cross section of these filaments. And by computing the emitted X-rays from this beam, what I find is that it emits very high power of X-rays. So you can see here tens to hundreds of megawatts during this interaction of X-rays. And the divergence of these X-rays is very, very low. So they are very well collimated. And so this high power X-ray source with very, very well collimated emitted X-rays is very useful for backlighting laser plasma experiments and imaging very high Z and very dense experiments. So on the right here, I have a comparison of the X-ray flux from this simulation, which is the dashed black line, with three other kind of leading X-ray generation mechanisms through short pulse laser plasma interaction. And so what you see here is a plot of the X-ray energy on the x-axis versus the flux on the y-axis. So this flux is the kind of the photons in an energy range over the angle of emission. So in these three different color regions, you see that the previous work had shown that different conversion mechanisms were most efficient. So these three mechanisms, ICS or inverse Compton scattering, as well as bremsstrahlung and Betatron emission. It turns out that this new X-ray source that I've been investigating could be better than actually all three of these over this entire energy range. And so there's a lot of interest in pursuing this further. And so with that, I'll then move on to the second part of my talk, where I'm going to be discussing, in this case, ion acceleration in laser plasma interaction. So laser-driven ions are very important for a number of applications. For example, in fusion energy science, these ions can be used to probe self-generated electromagnetic fields. Because they have charge, they will feel these electromagnetic fields as they pass through a laser plasma interaction, and also using it to study fusion materials, for example, or using it for proton therapy for medical purposes. And so there's also been a multi-decadal effort in advancing the studying how to get higher energy protons and higher fluxes, higher repetition rate for all of these different applications. One of the most interesting methods to generate laser-driven ions is called magnetic vortex acceleration. So in this proposed scheme, what happens is you have a kind of a thin slab of a fairly dense plasma. So in this plot, we have here this is kind of a cut through this plasma slab. You have roughly 30 microns of plasma here, and the laser comes in from the left side and then propagates through this plasma. The plasma is near critical density, so the laser it's just dense enough that the laser can barely propagate through. But because it is reasonably dense, the laser accelerates a lot of electrons and also ions as it propagates through here. And understanding the process by which these numerical simulations to understand this acceleration process have shown that we see here on the bottom rows that what happens is that you generate a very strong magnetic field in the bottom left here as this laser propagates through. The laser accelerates a lot of electrons, those generate a strong current, you get a strong magnetic field, and then as this current exits through the back of the target, through the back of the slab, you then generate a very intense longitudinal electric field. And so this electric field at the backside of the target accelerates the ions to very high energies, it is thought. However, this particular ion acceleration mechanism has been rather difficult to demonstrate in practice. Although the simulations indicate that this scheme should be able to generate very high energy ions, which you see here. So you have here laser power on the x-axis, ion energy on the y-axis, and it seems to indicate that for these types of laser powers that are routine in these kinds of experiments, that this acceleration mechanism should generate much higher ion energies than the dominant competing ion acceleration mechanism, which is TNSA, or target normal sheath acceleration. However, there have not been any demonstrated definitive experiments showing this. So as part of my work, we set out to study kind of the fundamental mechanism by which these fields are generated. So although it's very difficult to conduct these experiments with such a dense target, what we did in our experiment with my collaborators and in our modeling is, instead of using a fairly dense target with a density on the order of 10 to the 21 particles per cc, we used a much more dilute plasma of roughly 10 to the 19, so a gas jet again. And because of this, although you don't get, we don't expect to accelerate ions to very, very high energies, you can still accelerate very high energy electrons, and you can study on much larger scales the electromagnetic fields that are generated in this interaction. So by reducing the plasma density, the fields become weaker and much larger scale and much more slowly evolving. So they are much easier to probe with radiography. So in this experiment, we have a gas jet. We have a high power laser which strikes the gas jet and accelerates electrons. And then we also have a secondary laser here on the bottom left, which generates protons to pass through this interaction and kind of image these electromagnetic fields. And the secondary laser, it uses the more standard and well-developed method of target normal sheath acceleration to generate these protons. But the benefit of using a gas jet is not only that the fields are much larger, but also that we can create gas jets which have very sharp density profiles and contours, which you can see kind of in this profile here. So it's much easier to generate a gas jet with a sharp density profile on these millimeter scales compared to a very, very dense target on tens of micron scales. So these are 4 proton radiographs that were taken during one of these interactions, one of these experiments. In this image, you have the laser coming in from the left. The gas jet, you can sort of see the profile of it here. These images correspond to a region of space that's about 5 millimeters wide, and the gas jet opening is 1.5, so it's about a third, the middle third of the image is where the gas jet is. And you can see that as time goes on, you see this very large structure form in the exit region of this gas jet, so on the right side. And so this indicates that as the laser is passing through, it accelerates a large number of electrons. And then as those electrons leave the backside of the target, they create these very strong electromagnetic fields. And so we can use this information in the radiograph to actually estimate the strength of these fields and compare to models to better understand this interaction. So I also conducted particle and cell simulations of this interaction. What you see here on the top is the density of the ions, and in the bottom is the magnetic field that is generated. So this is a simulation just of kind of a reduced, slightly modified set of conditions to make it more feasible to simulate. But what you can see is you kind of reproduce the same picture that was seen in the previous simulation studies, but this time in a gas jet. So we see that as the laser propagates through, it kind of digs this channel in the ion density, and then on the right side, where the laser and the accelerated electrons are leaving the target, you generate this strong magnetic field and kind of a depleted cavity region, lower density in the ions. And so examining the structure of the electromagnetic fields in this region, we see that as time goes on, moving from forward in the different columns, we have the electric field on the top and the magnetic field on the bottom. And we can see that in this region where the magnetic field is kind of neutralized or drops off at the top of this cavity, we have a strong sheath electric field. And so it turns out that as the protons are passing through this cavity, because of the geometry, the magnetic fields actually don't deflect them very much. At the top of this cavity, the protons are traveling parallel to the magnetic field, so there's low deflection. But the sheath electric field is actually responsible for the structures that we see in these radiographs. And we verify this in simulation, that when we simulate these probe protons passing through the interaction, that we see qualitatively a similar structure, and we can identify that these structures in the radiographs do arise from this sheath electric field. We can actually relate the electric and magnetic fields through the simple principle that the magnetic pressure on the background plasma acts primarily on the electrons, but as it pushes them, they create a space charge electric field, which couples them to the ions. So with that, we can relate the magnetic and electric fields with this relation that you see here. And so when we look at the strength of this electric field and kind of this geometry, so the electric field has a sort of a ring-like structure. If you look at it kind of down the barrel of the laser. So in this cartoon here, the laser is coming out of the page. Then this ring-like electric field will actually create these caustics in the radiograph. The features that we see, and we can calculate with a simple assumption of an annular electric field, and using a well-developed pre-existing analytical method to calculate these, that we're able to calculate what kind of electric field will create those features that we see in the radiographs. And then based on the density of the gas jet, so the density drops the farther away you get, we can actually relate the electric and magnetic fields. So at these farther distances, away from the gas jet, towards the edge of the radiograph, we can infer that the magnetic field should be at least roughly 100 kilogauss, which agrees very well with our expectations and the theoretical models. And so in conclusion, we showed that high current laboratory electron beams can drive and study plasma instabilities relevant to gamma ray bursts, enable bright and compact X-ray sources, and we can study these processes in the laboratory, and we report what we think is the first demonstration of a laser-driven magnetic vortex in the laboratory. All right, thank you for your time.